Okay, as I said before, the title is the Fibonacci Bees algorithm for continuous optimization problems and some engineering applications. So first of all, I'd like to mention the first version of Bees algorithm proposed by Professor Pham in 2005, and it is now known as basic Bees algorithm. And various variants have published since then. And the one we taken into account will be the standard Bees algorithm for the comparison of our results, which is developed developed with new strategies, and you can find these in Pham and Castellani paper in 2009. And these strategies are shrinking and site abandonment. I want to mention these two, which is very important in our experimental setup as well, because we tried these, and I will mention those in the latest slides. So first of all, when we forage a patch, we send the certain amount of bees into the patch, and then there is no improvements on this one, and we are focusing on a smaller part in this patch, which means we shrink the size, and we now, with the same amount of bees, focusing on the smaller sites. And then when there is no improvement on this side again, and for certain limits, and we abandon this site and create a new patch. And it's a cycle in this way until the stopping criterion has met. Standard Bees algorithm uses 8 parameters. As most of you know, these are the Scott bees numbers, elite sites numbers, number of best sites, and recruited bees for both elite and best sites, and initial size of neighborhood, shrinking rate, and stagnation limit is added in this version. And now the Fibonacci Bees algorithm. I'd like to mention the Fibonacci first. Leonardo Fibonacci is a mathematician from 13th century, and one of his work is the Fibonacci sequence, which can be seen in the nature. And this is a natural phenomena, so it occurs in nature actually, and you can find it in leaf accommodation in plants, spirals in pine cones, and seed positions in sunflowers. And the bees are another example of it. So as you can see, the ancestral line of a drone, and it starts with in female bees as well. It starts with 0, and then it's after the generations created, it reaches the Fibonacci sequence. And in our algorithm, in Fibonacci Bees algorithm, we use less parameters than standard Bees algorithm, which number of Scott bees is the same with standard Bees algorithm. And we use selected sites and recruited bees for selected sites, and shrinking rate, also maximum revisit, which is similar to stagnation limit. So this is our flow chart. We first start with initializing, then we sort and create patches. We sort their fitness values and create patches. And as always, local search, then global search. And when we met the stopping criteria, we provide the best solution. But here in local search process, we are assigning an R number of bees to M selected sites. So if we have, for example, M is equal to 3 and the maximum NR number is 8, the all numbers is coming from the Fibonacci sequence. So the first patch will take 8 foraging bees, and the second one take 5, while the last one takes only 3 foraging bees. And this is the example of how we assigned our foraging bees to selected sites. And then the after fitness evaluation, we if there is no improvements in the patch, so we increase the revisit variable. Then if maximum revisit is achieved, we abandon the patch and create a new one. So we tested these algorithm on 10 different benchmark functions with 50 independent runs. We both used the 10-dimensional and 2-dimensional functions here. As you can see from the slide, Sphere, Eckley, Rosenbrock, Gree-Wang, Rasrigin was the 10-dimensional one, and Eosom, Schwefel, Goldstein and Price, Martin and Geddy and Schaeffer benchmark functions are used for testing these algorithms. And our stopping criteria was 500,000 fitness evaluations, or the accuracy of 10 to the power of -3. So and for all the tests, our total population is 105, which was the best performance of standard BAs in the mentioned paper. So in hypersphere, these are our results of our experiments. In hypersphere function, we were able to reach the 100% success rate, and to compare the standard Bayes algorithm, we get our fitness evaluations as well, and most of them not most of them, all tests was done in fewer fitness evaluations than the standard Bayes algorithm, because standard Bayes algorithm also reached the 100 success rate for this specific function. And similarly, we achieved this with Eckley, Schwefel, and Martin and Geddy as well. So our results, the results of Fibonacci Bayes algorithm, it showed 100% success rate with fewer number of fitness evaluations. Now the tough functions for our algorithm, one of it was Rosenbrock. So the success rate was very low in this one, and we couldn't achieve the accuracy for this function, but as you can see from the graph, it is close at some point when we increased our foraging Bayes. As you can see here, when we increase our foraging Bayes, we are getting closer to the results, although the stopping criterion is not met yet in terms of accuracy. Of course, the program stopped because of the number of fitness evaluations is filled. And Gree-Wang is one of the tough ones, and we achieved here more than 60% success rate, and this is again more than the standard Bayes algorithm. The standard Bayes algorithm achieved more than 250,000 number of fitness evaluations, and our results are under, except one population set, our results are under 240,000. So you can see the specific success rates of the specific population set as well. For rastering function, we have achieved almost 100% in specific populations again. When the foraging Bayes getting higher, it starts to find the global optima for that function, and the SPA wasn't successful in standard Bayes algorithm, wasn't successful in this one, and in total we achieved 48.66% success rates, and as you can see, we almost achieved 100% in specific populations. These are the other similar ones. These functions show the similar results as standard Bayes algorithm. So there's nothing specific to mention on that. And we also use the engineering optimization problems, which is one of the popular ones is tension compression spring optimization. As you can see, we have 3 dimensions here, and it's the diameter of the wire, diameter of the winding, and the number of springs active coils. So we successfully solved this one, where the global optima is here. In all populations, we've reached this number within the accuracy, within the difference of 10 to the power of -3, and our number of fitness evaluations are between around 8,000. So the second application of ours was welded beam optimization, and this is a 4-dimension, and this is a 4-dimension optimization problem in engineering applications. And as you can see, this is a minimization problem as well. So we have successfully solved this one as well. We used Fibonacci Bayes algorithm, and while there are some infeasible solutions for some populations, we in most population sets we reached the global optima successfully. In conclusion, we achieved a parameter reduction in standard Bayes algorithm, and the proposed Fibonacci Bayes algorithm outperforms standard Bayes algorithm, as you could see it from the results. And Fibonacci Bayes algorithm was able to find the solutions to both tension compression spring optimization problem and welded beam design optimization problem. And that's all from me. Thank you so much for listening me, for your attention. If you have any question, you can reach me by my socials and by email. Thank you.